This is a webinar on the NeuroNavigator. It's a new tool inside of NeuroGuide. It's also a standalone tool that you can purchase independent of NeuroGuide. So in other words, you do not need NeuroGuide, which is more expensive, to use this new tool. It represents the next generation of EEG neural imaging. And what we're going to answer or deal with in this practical webinar is how to use it and what is it. First, I want to give a little background. In 1990, basically, I went to the National Institutes of Health as a project manager for a 128-channel EEG system. It was the first in the world. And I was also part of the multimodal neural imaging team to cross and co-register different imaging modalities such as the PET scans, SPECT scans, structural MRI, functional MRI, magnetic electroencephalography, and EEG. And all of those were co-registered by a lot of effort over a number of years. And this is one book in 1994 that I edited that includes all the various methods and all the co-registration with the different imaging modalities. And we have 13 chapters on quantitative EEG and co-registration with the MRI and other imaging modalities. This effort came out of the Human Brain Project that was initiated at NIH after President Hubert Bush, first President Bush, designated the 1990s as the decade of the brain. And as a consequence, various government agencies from the Department of Commerce to the National Science Foundation to the National Library of Medicine to various parts of the National Institutes of Health came together, divided up parts of their budget to go towards the Human Brain Mapping Program. And I was proud to be part of that and happy to have worked with my colleagues to organize this large volume in 1994, published by the academic press. This is still available in unused form, but what we're going to be going through today is sort of a culmination of the distributed inverse solution of identifying the sources of the EEG by measuring the electrical energy or the electrical potentials at the scalp surface and using physics to identify the sources of the EEG that are in 3 dimensions inside the skull, in the interior of the skull. The second volume that came out in 1995 is Developmental Neural Imaging, in which we, again, put together all the various parts of this, of imaging with different modalities from birth to old age, and showed some of the ways that this neural imaging methodology is useful to understand the development of the human brain. Now, as a backup on this, to give you some context, in 1994, Roberto Pascual Marquis developed a method called Loretta, stands for Low Resolution Electromagnetic Tomography. It was what's called a distributed solution. It had 2,396 current or voxels, actually used the gray matter voxels of the MRI. And inside each of those voxels, a 3-dimensional current source was put in mathematically. The electrical potential is recorded from the scalp surface, and then the spatial relationship between the location of the voxels and the location of the electrodes allows one to derive what's called an inverse solution that estimates the current that's coming from each of these voxels that contributes to the surface EEG. It was called on the left side here, the Loretto viewer. It used an average brain. You can see here it's very blurry MRI from the National Institutes of Health. This is the axial, sagittal, and coronal sections. You can move around in there with the cursor and evaluate both raw scores and z-scores. It's very useful. It lasted from about year 2000, 2002 or so until today. However, it is not supported by the Key Institute no longer in Switzerland. It does not work with a lot of the graphics cards and various hardware that has developed since then, and it is not supported. So it really is, although useful, it's on its last legs And one of the motivations that we had to develop the new generation Navigator Reviewer was in recognition of this excellent work that Roberto Pascual Marquis had done and try to provide something that is even better. Now, the spatial resolution, the 2,394 voxels are in contrast to this on the right side. This is called SW Loretta, and I'll go through in a minute what that means. It has 12,270 voxels, and there's many more tools to navigate through the brain and to organize by networks, to look at both z-scores and raw scores, to be able to tabulate the magnitude of the z-scores or the raw scores, to sort them, to create images, to put into clinic reports or whatever, or research papers, or whatever you want. Now, very briefly, what is the inverse solution? If you look in the upper left, or actually the left panel here, this is an example of a three-dimensional source that could be an epileptic focus that has X, Y, and Z representation in vector calculus, and it has a resultant vector. And that's then you essentially what's done as an epileptic focus, like with 128 channel EEG, you've got a rough idea where that focus is, and so you mechanically move this three-dimensional voxel, current source, as close as you can to which you think is where the epileptic focus is, and then the program will do a min-max operation to move it closer to try to get it to maximize the current vector for that voxel or a set of voxels where the epileptic foci is. So you're really, with the discrete solution, looking for an epilepsy, looking only for one or two solutions. It's usually one, maybe three voxels, sometimes, three current density vector systems, or sometimes four, but usually it's just one or two with 128 or 256 channels. Just basically, you don't get much more than resolution if you go above 128. So that's called the discrete method, used primarily in neurology. The distributed method is seen here. It was used in cardiology at the turn of the century, the early 1900s, in which now you have inside the brain a whole large volume of current densities. A lot of these little X, Y, and Z current representations now are inside each of the voxels. In the case of the Key Institute Loretta, there was 2,396 of these little three-dimensional sources inside each of the 2,394 voxels. And so it's different than the discrete in that you have quite a large number of dipoles, and you're able to use linear algebra actually to derive the best fit. Now, the key to this is what's called the lead field. This is a spherical representation of the scalp and the skull and the brain inside with different conductivities. And imagine if you were to put a battery inside here and move it around with sensors measuring the electrical potential at the scalp surface here. As you moved the battery, the positive pole of the battery to here, you would see a very large electrical potential at that point, negative, and there'd be negative potential down here. And as you rotate that battery, you would see the electrical potential also that's moving, and that would be what's called the forward solution. That is actually you insert and put a current in the interior of the brain or interior of a volume. This could be a balloon with sensors on the outside, and you move that source of the electrical potential around, and the predictability of what the potential will be at the scalp surface is extremely high. That was used primarily by Clerk Maxwell in 1864 with his treatise on electricity and magnetism, and then von Helmholtz in the 1870s, who then developed this concept of the lead field, in which you had the forward solution predicting where the magnitude of the electric potential would be. But von Helmholtz went further and he developed the inverse solution, in which is over here. If you have the electrical potential, essentially you got K is the weighting of the lead field. But if you have measured the electrical potential, you can move K over to this side and divide it into E, and then calculate J, which is the current sources, inside each of the 2,394 voxels, or however many voxels you have. So it's a linear function. Once you know K, which is really a spatial relationship between each voxel and the sensors at the scalp surface, and you know the electrical potential, the J is the unknown, you can divide K into E and get J. So that's how you get the current densities inside of each of the voxels. It's the inverse solution. And there's a lot involved in the mathematics of that. You have to have physiological constraints, otherwise there's an infinite number of solutions in vector calculus when you divide by a value have an inverse. So you constrain it in a variety of ways. Roberto Pascual used the Laplacian transform. We're not going to go into details on that. That has to do with the smoothness of the current density. It makes assumptions about simultaneously active generators so that neurons actually cooperate in large numbers to generate currents in synchronous groups. And if you make that assumption, then the Laplacian is one of the physiological constraints that allows you to get an exact linear solution to that equation I just showed, because it is consistent with the underlying physiology, that is, in the underlying way in which neurons behave. The initial or first Loretta in 1994 up to about 2000, and S. Loretta has the same problem too, but is biased due to the head model and the lead field because it used a spherical head model, and it's not a homogeneous field. It's an adjustment to help deal with that mismatch. Although Loretta is still quite useful, it is not as good as S. Loretta. S. Loretta gives you zero localization error, and it divides the standard deviation of each of the voxels of the entire volume into the voxels. And so it's like the functional MRI, which gives you a probability measure, essentially, of the currents that are being generated inside or the amount of blood flow that's going on inside a collection of voxels, in which the variability of the sources is important. So, for example, if you have a lot of current density in a small area with low variability, then you will see it. If you have high current density in a particular area with high variability, then you will not see it. The same with functional MRI. You have a high variability in the blood flow changes in the experiment. Even if the magnitude is high, you will not see it. You will see it if there's low variability. So it's a probability estimator, and that standardized Loretta, and that's why the S is there for standardized Loretta. And it helped minimize the bias due to the spherical head model. A Z-score Loretta is what we use. We divide each voxel by the standard deviation of currents that were generated from a large population of normal subjects, and it also gets rid of the bias by the spherical head. And then finally, SW Loretta, developed by Ernesto Soler, is one where he starts with S. Loretta, but he uses a realistic head model or a realistic MRI. It's no longer an average. And then he weights the sources by making sure that the lead field is homogeneous. So he has a transform matrix that takes all the voxels, because they're quite heterogeneous. There's different tissues inside the brain, and by moving or just essentially using a transfer matrix to make it homogeneous, he gets better resolution in the depth. So you can look at the whole cortex from the top layer, layer 1 through layer 6, excuse me, and get an idea of what the density of currents are in these varying depths. You cannot do that with S. Loretta. You can only do it with SW Loretta. Another thing is that SW Loretta does not use a spherical head model. That is, it's a sphere that you shrink onto the scalp, because the brain is actually shaped like a loaf of bread. It's flat on the bottom, and it's elongated, ellipsoidal. So it mismatches that model. One way to deal with that is to measure an actual real MRI brain and look at the boundary of that brain and all its shapes using the boundary element method. So you tensillate, put little triangles all over the surface, the actual surface of a real brain. So it's not a sphere, it's actually the shape of the brain. And that forms the boundary solution for the inverse solution, the boundaries for the mathematics of the inverse solution. And it is much more accurate. So there's another level of accuracy improvement with this 21st century NeuroNavigator using Loretta. This is an example of the various ways that the 2017 SW Loretta differs from the Key Institute Loretta or even the Loretta. The Loretta at the Key Institute uses, I think, around 6,200 voxels. But there's actually now we pared it down to 12,270 voxels because we limited to just cortex, and actually we also have the thalamus, but there's no cerebellum or basic ganglia, etc. And so there's a lot of ways that it improves. There's things available. There's in the NeuroNavigator that are simply not available in the Key Institute Loretta. So conclusions are that SW Loretta improves the localization properties of standardized Loretta. SW Loretta is able to reconstruct sources under real conditions in the time and frequency domain. And it is in applied neuroscience is created, essentially used SW Loretta as an engine inside of a NeuroNavigator environment that allows you to take advantage of the special mathematical properties of SW Loretta and navigate through the brain and through different slices and different volumes and look at different connectivity and coherence between Brahman areas or phase differences, both lagged coherence and regular coherence. So one can adjust for the influence of volume conduction. So there's a number of important advancements. So what I'm going to do now is take you through the NeuroNavigator. We're going to start with a patient, and we're going to step through it and try to answer questions about how do you use the NeuroNavigator. We're going to do it in two parts. The first part is going to be in the current density itself. That is just how much current is being generated in different parts of the brain. The second is the tools inside the Navigator that allows you to evaluate functional connectivity. That is the degree of coupling between Brahman areas, both for coherence and for time differences or phase differences. So let's escape from our PowerPoint, and we're going to launch the NeuroGuide, and we're going to take a look at this. This is a demo in NeuroGuide. This is a patient struck in the right parietal region by a bat, was assaulted. And the way that you use SW Loretta and the NeuroNavigator is you start with patient symptoms. In this case, this patient has spatial neglect. The patient cannot write on the left side of a piece of paper. The patient does not shave the left side of his face, and he has paresis on the left side. And when we do the quantitative EEG, we're very careful to make sure we edit the EEG. So we select artifact-free segments. We have both automatic edit tools that help you identify potential, it's very, very conservative, drowsiness, eye movement, muscle, stuff like that. So it will eliminate those types of artifact, and the user can make sure there's at least 0.9 retest reliability. In this case, we got 0.98. We have 1 minute, 55 seconds of EEG, and up here is the power spectrum, and here are the Z-scores. And you can see that there's, on the left side, there's 4.61 standard deviations in C4, 3.22 in P4, and 4.32 in T4, 2.549 standard deviations outside of normal in T6. It's all in the right hemisphere, consistent with the CT scan and the known pathology or abnormality or history of this individual. We can also predict which Brahman areas will be significant from deviance before we launch the NeuroNavigator. You move your mouse or your cursor to the label on the left here, and I right mouse click, and it shows you the problem areas you're predicting that will be deviant from normal. So I'm going through here to identify those likely Brodmann areas. That way you can form hypotheses prior to launching Loretta or launching SW Loretta or the Navigator, and avoid multiple comparison issues. So you've got the patient's symptoms, you evaluate the surface EEG to see to the extent you can link the symptoms to deviation and areas of the surface that are linked to the symptoms. And then now we're going to drill down into the brain to see to what extent we can link the patient's symptoms to dysregulation in hubs and nodes and the connections between the hubs and nodes inside the brain. So to do that, I've already launched SW Loretta. I'm going to minimize that display, and I'm going to bring up what you will see when you launch the NeuroNavigator. One thing I want to show before I do that is how to launch it. You click Analysis, NeuroNavigator, and generate new data. You can do either z-scores or raw scores, but that's how you get it to work. And so let's expand SW Loretta. This is the default view that comes up. Essentially what we have here are the axial or horizontal slice. This is the sagittal slice, and you can navigate, as you can see I'm doing, and that is the coronal slice. Then you have a rendered head as well. Now, under the cursor, there are values that tell you both the telluric atlas coordinates. That's the common coordinate system for all imaging modalities. When they're co-registered, tells you the Brodmann area and the value underneath that cursor. We can jump to, if we want to do right now we're set at 1 cycle per second. We're going to change it to 5 because we knew that 5 cycles per second is where the greatest deviation from normal was, or the area linked to symptoms. You can jump to maximum, you can jump to minimum. You can have a fixed point as you go through the brain under different frequencies. You say you just fix the point in the hippocampus and you go from 1 to 30 hertz. You'll see what's happening in just the hippocampus across all the frequencies. Or you can jump to the extreme, whether it's positive or negative. I'm going to leave it there. This box here duplicates the box that's up here, but we're able to do a right mouse click and copy the image that's up there or copy the information in this text box. We can do that wherever we put our cursor. So you're able to put that now into a clinic report if you wish. I'm going to move up to 5 cycles per second because that is the frequency that we found most deviant from normal. And what we're going to do now is look at the current densities. If we want to evaluate the current densities, what we're going to use are the controls that are in this first row of controls at the top here. We can look at the axial view. We can still navigate and look at the z-scores change in that view. We can do the coronal view, sagittal view. We can do a volume view, so you just look at the volume. We can look at the axial, horizontal, and sagittal, just like the Key Institute, but with much more navigational power. And then you can look at all 4 slices, like is the default. And then you can also do all slices, which gives you all the slices from the depth up to the surface, and you can move these around and still get values that you're interested in. So I'm going to go back to that. The first thing we want to do is adjust our thresholds for either the raw or the z-scores, and we do that by clicking on current source density scale. And this control box comes open, and here's the z-scores. We're going to look at the z-scores from, let's say, 2.5 to 4 standard deviations. And those are z-scores that are inside, actually, these voxels, which is what we're going to look at. We could change that to look at more or less, but we'll just do this so we know we're getting the most important parts. And we can see here, if we click here, you can see that is 3.24 standard deviations outside of normal, so it's reasonable to keep this set that we're looking at here. Now we can also adjust for our scalp scale. That's the electrical potential that's actually on the scalp. You can see it here. That's the electrical potential. I can vary that. That's the z-score. And we can either get rid of the scalp model or bring it in up in this upper row. And I'm going to go through that in a minute. But that allows you to look at the electrical potential at the scalp surface in terms of z-scores. There's the right parietal region at the EEG on the scalp surface, as well as simultaneously evaluating the brain itself that's in the interior. And we have other controls we're going to go through in a minute to look at other aspects of that. Now, what we want to do, so we've got our scale set that's reasonably set for both the cortex, current density, and the electrical potential at the scalp surface. Now, we can look at these things in different ways. I'm going to just close these for now and go next to settings. So we did current source density scale, we did scalp scale, and now we're going to look at settings, which controls a number of different things. One is the general color of the theme. We can make that light gray, click apply, or we can make it dark and click apply. This really pops it out, allows you to see things in greater detail than I just clicked on the head model, and we're going to go through that in a minute, than you can when it's just light. We can also look at, if we want to get the orientation right, you can click orientation. I'm going to look at just the right hemisphere, and then you'll jump to the right hemisphere. I want to look at just the left hemisphere. I can jump to the left hemisphere. If I want to look at the front, I can do that. If I want to click at the back, I can do that, etc. So you can jump to as beginning points as you navigate through the brain using that control. You can change the transparency of the cortex. Right now it's 0 transparency, but if you can make it 50% transparent, you can see there's a little less of it. I'm going to make it 0 for now. You can now control the transparency of the scalp map. I can make it 0% transparent. Now it's very distinct where the electrical potential is. You can also look at the Laplacian of the electrical potential. It's the currents at right angles through the skull. And you can change the z-score, and you can see there's a coup contra coup kind of damage that's done that you did not see just with the electrical potential. And you can, again, set the settings by going to scalp map scale and change the settings for the z-score Laplacian so you can get it more localized or as you wish to make it, as we did before. Now I'm going to make the transparency of the scalp 50% so that we can still see the brain and go through it. Now we can create what's called a head model. In order to activate the head model is now activated, I can deactivate the head model. Here's the head model. I'm going to make it 0% transparent. And now we have the head model and the scalp model. If we want to look at we can create planes inside here and navigate using cutting tools through this head model. The way we do that is we have an axial slicing tool. So now I'm jumping up to this top row. And we're going to go back down to the second row in a little while, a coronal slicing tool, in which case we are moving now with these slicing tools, and we can see them best by getting rid of the head model and then moving through the slicing tools that you can see here. This allows you to see the slices of the brain in different three-dimensional views. So you can see where things are maximally deviant. It's a navigation tool that allow you to look at this in more detail. Now we can also do what's called a cutting box. That's up here. Click cutting box. And then let's put the head model back in. And now let's come through it. So now you're slicing through the scalp, the brain, and the skull all at the same time. We can get rid of the scalp map by deselecting it. And then we can navigate through the brain as much as we wish, evaluate these different slices with these slice cutting tools. Now, if we want to just look at the slices and nothing else, what we need to do is make the cortex completely transparent, or just deselect the cortex. Now we're looking at just the slices. This is the sagittal slice. It corresponds to this slice. I'm going to move it up a little bit. Here's the axial slice that corresponds to this axial slice. Here's the sagittal slice, corresponds to this sagittal slice. So you can look just at the slices, if you wish, to look at these surfaces that are deviant from normal, identify them, put your cursor where you want, get rid of the head model if you wish, and read out what the values are in both at the upper left and the box down below. Click right mouse click, copy the image, etc., and then put that into a report. You can always go back to the theme, change it to light if you don't want to waste ink. So you can do all of those things quite easily by running through this cutting box. We can also, if we bring back the head model, we can look at just the left hemisphere like this and then go through it this way. Or we can look at just at the right hemisphere. We can look at the back of the brain. Etc. And then we can bring the head model back in and evaluate these various features with the head model there as well. Now, what we want to do next is deselect the slicing. Here you can see just one slice. Or you can look at just that slice. That's the coronal slice. And of course, you got all of them if you want. And then we'll bring the cortex back so you can see the cortex as well with the landmarks. And then the head model will go from bottom, and then we come back up with the head model like we were before. You can also do up here in the upper top controls are you can save all of these 12,274 values in a file for 30 frequencies, so it's 30 columns, and then 12,270 rows. Those are tab delimited. You can do a lot of different things with it statistically, or export it into other programs. This is a binary file called the .so5 file that's used for neurofeedback. You can save that and then import or load this file into Z-score Loretta, the NF2 Loretta neurofeedback module inside of NeuroGuide based upon your findings in this display. Now we also have over here on the right all the Brahman areas from 1 to 48. We can sort them by number, so they're numerically 1 through 48, and you can see which ones are significantly deviant. These are the center values, are all right hemisphere, because there was no damage on the left. We can sort by left and right hemisphere. We can sort just by the value, the Z-scores in the center voxel of each of the 48. It's really so there's 48 voxels, so that we can look through all of those, or 48 Brahman areas, and number them in whatever way we wish. We also have the ability to look at networks. Here, for example, is the addiction network, and it's useful to turn on Show Atlas so you can see the boundaries of Brahman areas that comprise the addiction network. Now, this individual did not have addictive problems. Or you can look at the anxiety network. You can look at the default mode. Salience, etc. So there's a large number of networks in here from various parts of the scientific literature that came out of the Human Brain Mapping Program with several billions of dollars internationally, went into the creation of this large consortia of scientists collating their data and co-registering it to a common telluric atlas coordinate system and creating a lot of uniformity independent of the measuring modality itself. These are a lot of functional MRI based networks and PET scan networks. The Hagman hubs are networks derived by diffusion tensor imaging. That's a type of structural MRI. And then there's also diffusion tensor imaging atlas that you can evaluate. Frontal atlas, the occipital, etc., based upon the Catani and Deschatten diffusion tensor imaging atlas. You can look at tinnitus, etc., and evaluate the deviation from normal with patients that have tinnitus, identify those nodes that are most deviant from normal, and then use neurofeedback to reinforce those nodes towards a greater stability and efficiency as one evaluates the severity of the symptoms. The goal is to reduce the symptoms. Then you also have a symptom checklist. You can look at addiction. These are all, there's chronic pain, this is the pain network, etc. And evaluate, based on the symptoms, the parts of the brain that are likely linked to those symptoms. And in terms of the current density of what we're looking at in this particular part of the Navigator. Now, the second thing we're going to look at next is connectivity. We have functional connectivity working at this time. In the near future, we're going to have effective connectivity, which is information flow. It's the magnitude and direction of information flow. And then the final is we're going to put diffusion tensor imaging images themselves inside the Navigator so you can link together the diffusion tensor imaging structural MRI with the functional properties of networks as well as the current density generated inside these voxels, and then of course at the scalp surface, which is the EEG. So in order to evaluate connectivity, number one, let's get rid of the head model. Let's get rid of these slices. I'm deselecting the slices. We have the brain here. I'm going to set up the cortex so that it is 50% transparent. I'm going to select a network. In this case, it's the addiction network. And then I'm going to say, show me the center voxels. That's this control up here, center voxels. And then I'm going to look at connectivity between the center voxels. Okay. We can make the cortex 100% transparent. And now we just have the network. We can change the strength of those connections by going to connectivity scale up here. Remember, we did the current density scale, did the scale at the scalp surface. Now we can change the connectivity scale. These are z-scores. We want to see all of them. Let's go all the way down so we're looking at every one of the connections. It's a lot of them there. I think I'm going to go with networks over to anxiety. There are fewer of them there. But there's the connections. We want to know, now you have your ability to look at the volume view here. You can change the size of the network by your mouse roll bar, center bar, the wheel, mouse wheel. And in order to identify what Brahman areas are these, you press Shift key and then right mouse click. You'll see that's Brahman area 21. Okay, and you have a little label here that's next to Brahman area 21. What is this Brahman area? I Shift key, right mouse click, it's Brahman area 10 left, Brahman area 10 right, Brahman area 13 right. Now in the connectivity world here, under connectivity in the settings config dialog box, you're looking at coherence, but you can also look at phase differences. I'm going to go back to coherence for now. And you can evaluate the connectivity by controlling this control. Now, if you want to look at the labels, all the labels, you click Show Labels, click Apply. And now you got the labels for all of the Brodmann areas. And if you want to bring the cortex back, we're going to go to cortex and put it at 50%. So we get the landmarks of what we're looking at for our connectivity. This happens to be coherence, which is functional connectivity. You, of course, can get rid of those labels if you wish. Clicking center voxel and deselect Show Labels. And we can put slices in. And we can also do a movie. So first we saw we can save files, but we can do a movie. This is a 500 millisecond step through the movie. It will start with 1 hertz, and then it will go through the brain at 1 hertz. You can put the head model back in. We can make the head model more transparent, say 50%. You can switch over to the 4-view, make that a little bit smaller, etc. So those are the tools that we can use. I can close out the movie or stop it anytime you want. Set 30 cycles per second. Now I'm going to go back to 5. So that you can see the connectivity, you can see the current densities. We can activate our scalp model. You'll see where the current density is deviant from normal. The connectivity, see where it's deviant from normal. You'll need to make more transparency changes in the head model to do that. I'm going to make it 70% transparent, or just get rid of it. And get rid of the scalp model. And then look just at the connectivity and get rid of the cortex and see where the slices are with respect to these Brodmann areas linked to the patient's symptoms. So all of these, so now this is the tutorial on connectivity coming near the end, but these are the tools you have available. You can take videos of this yourself. You can save any of these images at any time. You can look at just one plane and nothing else. So I'm going to deselect the coronal plane, sagittal plane. And I'm going to do the movie. As you step through the plane, you'll see how the nodes are different from the plane, from the axial plane in this case, at different frequencies as we're marching through from 5 to 6 hertz. So I'm going to stop this. So these are some of the tools you have available to navigate through the brain using the NeuroNavigator. On one hand, you have current density with networks linked to symptoms, and the other hand, you have functional connectivity and other types of connectivity in the future.